This system projects a 256 petabyte virtual address space into a mere 4 gigabyte physical mirror. It is called the consensus hypervisor. Standard Type 1 hypervisors rely on linear translation, allocating discrete physical RAM blocks for every guest. The consensus model overlaps thousands of transparent memory layers into a single pool. This bypasses the von Neumann bottleneck. Processing remains localized within the mathematical coordinate space. It operates through pace expansion and deterministic data projection. Data is generated mathematically at the exact coordinate it is requested, rather than retrieved from static storage. The system functions as a topological lens, observing these coordinates as a continuous manifold rather than a series of temporal memory buckets. On paper, this mathematical model yields O of 1 state branching and a 1,000-to-1 compression ratio for structured operating system data.
The difficulty lies in forcing this high-dimensional theory onto the rigid, physical constraints of x86 and Arch64 hardware. Legacy architecture actively rejects non-standard paradigms. This developer log captures a massive regression, a direct failure where the hardware forced the model back into standard, safe coding patterns. That hardware rejection creates severe cache latency, symmetric multiprocessing race conditions, and kernel panics caused by inflexible silicon memory mappings. Achieving this on classical hardware requires surgical C++ engineering, resolving hardware faults and memory conflicts at the instruction level to maintain a non-standard logic paradigm. The first major obstacle was the pace expansion bottleneck. Under heavy I/O loads, the deterministic memory projection experienced significant cycle drift. The CPU became temporally locked, waiting for the heavy emergence factor hash math to resolve before passing any data to the guest operating system.
The team implemented speculative topological execution, which decoupled the address engine from the verification controller by splitting them into parallel tracks. Core 0 now acts as a branch predictor, projecting probable data states using 10-bit routes directly in the L1 cache without waiting for verification. Core 1 follows asynchronously, performing the actual hash verification. If a state mismatch occurs, the hypervisor detects the error a few cycles later and triggers a state machine rollback. Decoupling these operations hides the projection latency from the guest operating system, allowing memory access to reach zero wait state bus speeds. Even with decoupled cores, utilizing static 10-bit chunks for memory mapping presented a structural vulnerability. Static memory addresses recreate the very von Neumann predictability the architecture was designed to avoid, leading to hardware prefetcher failure and cache thrashing. The developers introduced address bit dynamicism, a zero-cycle XOR logic injection directly into the core traversal loop. The data route now mutates based on the resonance of the payload itself. By XORing the static address bits with the payload of the current node, the path becomes entwined with the data it carries. This entanglement makes external reconstruction of the memory state mathematically impossible. It enforces isolation through high-entropy noise rather than software permissions, all with zero extra cycle overhead. Operating at ring 0 exposes the hypervisor to unforgiving hardware traps. The first was a critical memory exhaustion bug. The initial bump allocator pushed memory pointers forward without ever freeing them. During dynamic string generation, it bled physical RAM until the hypervisor hit a hard kernel panic. They replaced it with an SMP-safe buddy and slab allocator, using bare metal atomic spin locks to manage physical page reclamation across multiple cores. The second trap was synchronous I/O. A polling loop on the AHCI bus was stalling the entire system every time a virtual machine requested disk access. The team removed the polling loop, wiring the AHCI host bus adapter directly into the hardware interrupt descriptor table. This asynchronous DMA pipeline frees the processor to handle background face folding, maintaining compression without stuttering the guest systems. The final critical trap was a ring 0 FPU exception, caused by using double floating point math in the cryptographic key generator. On bare metal, floating point registers are not initialized by default. Requesting an XMM register instruction before the control registers are configured causes an immediate hardware panic. Solving these specific silicon plumbing issues, like converting the key generator to strictly 64-bit integer math, is required to move this topological theory into a production reality. Consider the logistical strain of 1,000 virtual machines attempting to boot and load the exact same system library at once. In a legacy architecture, this causes a massive write collision, choking the hardware bus with 1,000 identical requests. The Phoenix architecture uses a harmonic convergence engine to intercept these simultaneous DMA write collisions before they hit physical RAM. It executes a sidestep operation. The engine detects the collision, writes the transition once, and dynamically links the virtual machines to that single physical resonance. This transforms a fatal race condition into a real-time, zero-latency deduplication engine. The speculative pipeline, IDT-wired HCI, and convergence engine form a hardened bare metal framework, creating a ghost city. A master basis runs at the core. Guest VMs exist as entropy residues, mathematical differentials branching off the master, consuming zero physical RAM until they diverge. This marks a paradigm shift from traditional isolation by boundary to isolation by resonance. The hypervisor treats system RAM as a unified field of kinetic data. The data materializes only when a guest CPU provides a fractal derivation that resonates with the specific harmonic filter of that manifold neighborhood. By utilizing this resonance discovery, the system achieves O1 scaling and massive density collapse on legacy hardware. This shift to topological mapping allows classical silicon to resolve complex state management with the efficiency of a quantum manifold.